Ever wonder what makes something like ChatGPT, well, work? How is it even possible? Believe it or not, a huge chunk of the answer goes back to a single research paper from 2017. It didn't exactly make a splash with the public back then, but it laid the foundation for the entire AI revolution we're seeing today. So let's pull back the curtain on this absolute game changer. Attention is all you need. To really get why this paper was such a big deal, you have to understand the huge wall researchers had run into. The central problem was this: how do you get a machine to grasp the entire context of a long piece of text? Not just a sentence, but a whole book, all at once. How do you get it to stop reading word by word like a person and just see everything? All right, so here's our roadmap. First, we'll talk about that big roadblock, what we call the sequential bottleneck. Then we'll get into the paper's wild new idea and take a look under the hood of the transformer it introduced. After that, we'll see the jaw-dropping results it got, and finally, connect the dots from this one paper straight to the AI in your pocket today. Okay, let's rewind the clock. Picture the world of AI before 2017. The main way we taught machines to understand language was with something called recurrent neural networks, or RNNs, and they had one massive built-in problem. You see, RNNs had to process language the same way we do, one word at a time. This created a huge bottleneck. Not only was it painfully slow, but the model would often forget the beginning of a long sentence by the time it got to the end. It's like the further apart two words were, the harder it was for the model to see the connection between them. And this slide, wow, this really spells it out. On the left, you've got the old way. The model has to chug along, word by word. The longer the sentence, the longer the path, and the more information gets lost. But look at the new way on the right. It's not a slow march, it's a flash of lightning. It connects every word to every other word instantly. The path length is always just one step. This wasn't just about speed, it was about enabling a whole new scale of model that was basically impossible before. Which brings us to June of 2017. A team at Google drops this paper with a title that was as bold as it was brilliant. They weren't just proposing an improvement, they were proposing we tear up the old playbook and start over. This quote right from the paper's introduction says it all. They basically said, you know these complex, one-word-at-a-time models? Let's throw them out, completely. Their radical proposal was a new design, the transformer, built only on something called an attention mechanism. It was a total break from the past. So what is this magic ingredient, self-attention? Well, think about it like this. If I say, the dog chased the ball until it got tired, your brain instantly knows it refers to the dog, not the ball. Self-attention is what gives an AI model that exact same superpower. For any given word, it can look at every other word in the sentence at the exact same time and figure out which ones are most important to understanding its meaning. Okay, cool idea, right? But how do you actually build a machine that can do that? Let's pop the hood and take a look at the architecture they designed. It's actually a really elegant and clever system. So at a high level, the transformer has two main jobs. On the left, you've got the encoder. Its mission is to read the input sentence, let's say in English, and create a really rich mathematical understanding of it, capturing all the context and relationships. Then, on the right, you have the decoder, which takes that rich understanding and starts generating the output sentence, say in German. And the engine driving both of these parts is something called multi-head attention. Now, this is so cool. It's like having a team of 8 different experts, or heads, all reading the sentence at once. One head might be a grammar expert, figuring out which words are nouns and verbs. Another might be a context specialist, linking pronouns to the things they refer to. A third might be tracking cause and effect. By letting all these different heads analyze the sentence simultaneously, the model gets this incredibly deep, multi-layered understanding of the text. Okay, but wait a second. This brings up a huge question. If you're looking at all the words at the same time, how on earth do you know the difference between the dog chased the cat and the cat chased the dog? I mean, the word order is everything. It completely changes the meaning. The solution to this is just beautiful. It's a trick called positional encoding. Before the words are even processed, the model adds a unique mathematical signature to each one, like a little timestamp or a zip code. This code tells the model exactly where each word is in the sequence, first, second, third, and so on. So it gets all the benefits of parallel processing without losing that crucial information about word order. So the theory was sound, the architecture was brilliant, but did it actually work? This is where the paper went from being a clever idea to a genuine revolution. the researchers put their transformer to the test on some of the toughest machine translation benchmarks out there. And the results? They were an absolute knockout. This table shows something called a blue score. It's just a standard metric for translation quality. The higher the number, the better the translation. Just look at the English to German results. The previous best model scored a 26.3. The transformer came in and scored a 28.4. It set a new state of the art. This wasn't a small improvement. This was a giant leap. Now, to put that into perspective for you, a 2-point jump on a benchmark like this is absolutely massive. It's the kind of jump that can take an entire field years of slow, steady progress to achieve. This result sent a shockwave through the whole AI research community. It was a mic drop moment. And here's the real kicker. Not only did it get better results, it did it while being way, way more efficient. The paper states it required significantly less time to train. We're talking 3.5 days on 8 GPUs, a tiny fraction of what the older, clunkier models needed. So you've got better, faster, and cheaper. That's the holy grail. Honestly, it's impossible to overstate the impact of these results. The transformer wasn't just a slightly better way to do translation. It was a brand new, powerful, and incredibly scalable building block for all of artificial intelligence. You can literally draw a straight line from this paper to today. A year later, Google used the transformer to build BERT, which totally changed how Google's search works. Then, of course, OpenAI used it to build the GPT series, which showed the world what generative AI could really do. And today, the transformer is the foundation for pretty much every major large language model you've ever heard of. So, when you boil it all down, what's the legacy here? Well, this paper broke the chains of slow sequential processing. That, in turn, allowed us to train models on a massive scale. It became the blueprint for everything from BERT to GPT, and in doing so, it single-handedly unlocked the age of generative AI that we are all living in right now. And that leaves us with one last, really fascinating thought. This simple, elegant idea, attention, was the key that unlocked this entire revolution in AI. So the question we have to ask now is, what's the next attention? What's the next fundamental breakthrough that will seem so obvious in hindsight and will spark the next generation of artificial intelligence?